Hello, and welcome to this introductory video on electric potential energy. In this video, we're going to introduce this idea of electric potential energy, discuss sort of where it's coming from, and then motivate how you might actually calculate it. And then we'll explore it a little bit further in subsequent videos. So far, as with many of these videos, you've seen us compare gravity to the electric equivalent. And we said gravitational force had the same form as the Coulomb force. Now, another feature of the gravitational force is that it is in fact a conservative force, meaning that the change in the gravitational potential energy associated with that gravitational force was not dependent upon the path in which you actually moved your object. So it turns out, you can convince yourself of this, that it is also true for the electric force. The Coulomb force, just like the gravitational force, is a conservative force. And whenever you've got a conservative force, it means there's an associated potential energy. So that energy is the electric potential energy. And that potential energy, as just like in the case of gravity, is going to be equal to the negative of the work done by the associated force. So the Coulomb force does some work as you move a charge from one point to another. That work is the negative of the potential energy that you end up storing. So if I take a positive charge and I move it closer to another positive charge, you know, and I know, that that thing is going to want to repel, and so if I let it go, it will move back away. So if it's going to move away, it's clearly got some potential energy. And me bringing that charge closer, the displacement was towards, and the electric force, the Coulomb force, was away. So that thing, the electric force, was doing negative work as I moved the charge closer, which is why there's an overall minus sign in the expression, because then that negative work amounted to positive potential energy. I was increasing the energy of that system because, as I said, if I let it go, it's going to want to fly back away. This is describing it in terms of the Coulomb force, but we also know, right, that the Coulomb force is sort of a way of testing what the electric field is doing. So I take my test charge and I put it there, it'll experience the Coulomb force, but that's really a result of the fact that there was an electric field. So we could also say that W electric is really the work done by the electric field of the original charge acting on that second charge. Okay. Now once you phrase it like that, it's not surprising that then we can write that the work basically is going to go something like Q times E times D, and it's in fact exactly this if the field is a constant field. So if we have a nice uniform constant strength electric field, then as you move across it in some distance D, the work is going to be Q times E times D. Okay, so basically this would be a sort of way of calculating what's going on with the potential energy. So I want you to think about some things. There's some interesting ideas here. So we know that the work done is a bit tricky because really the Coulomb force, if I'm only thinking about two charges, I know that's not a nice uniform electric field like we just ended with in our discussion, but instead it's this force that varies as 1 on r squared. So that's quite tricky to deal with because it's changing all the time. But if you are comfortable with some calculus, then you could actually work out what the work done by this Coulomb force as it moves some charge around and arrive at an expression for potential energy. So if you would like to try that, that's something that you could do. Otherwise, if not, then think about the constant force case where the field is nice and uniform so that the force is always just Q times E. Convince yourself at least that the work is indeed Q times E times D in that case.